Okay, good afternoon, everyone. Let's start. So last lecture, we have introduced the details about sum product algorithm, right? The key idea is to smartly leverage the distributed law, right? So if you want to compute the marginal distribution of one node in your graphic model, the naive way is just to, first multiply all the factors in the factor graph. Then outside this product, you marginalize over all the remaining variables. That is very inefficient because you kind of like combinatorially enumerate all possible configurations of x1, x2, x3, and so on, right? And you add all those combinatorial terms together. So according to the distributed law, if we can smartly leverage this law, we can first do the summation within a small range, right? And separately, and then multiply them together. In the sum product algorithm, we assume that your graphic model is a tree structure. So the key idea is that if you, this is your root node of the tree, right? So, and associated with each root node, associated with the root node is a set of factor children. Right? So this factor also serves as the root of the subtree. So the benefit of the tree structure is that those subtrees are non-overlapping, meaning that any node in this subtree, no matter it is a factor node or variable node, they will never show up in other trees. So they are non-overlapping, otherwise it won't call a tree. And that means if we do the summation outside of all the product, it is equivalent to first to do the summation inside each subtree, and then multiply the summation of subtree results together. And because those factors and variables in different subtrees are overlapping, so their summation can be conducted in parallel. They're not independent. They're not dependent on each other. In this way, we can largely reduce the computation. Right? The whole sum product algorithm is essentially to apply this distributive law according to subtree structures recursively. Because when you compute the summation inside this subtree, you can take a look at the factor nodes children. Now they are all variable nodes. And those these variable children, they also serve as roots of a series of non-overlapping subtrees. That means you can decompose the summation inside each subtree accordingly. You do it again and again until you reach the leaf nodes. Then we give the definition about the messages, right? The message is essentially the summation results over one subtree, right? And of course, depends on the direction of message. You might have message sent from factor node to variable node. You might have message from variable node sent to a fact node. But both calculation rule, calculation rule for both messages are just to follow the idea of this decomposition structure. Right? So, and also we talked about a simple yet very convenient way to implement this sum product algorithm, right? We first organize the whole graph as a tree, and then we first conduct messages from leaf nodes all the way up to the root node, and then starting from root node, we distribute a message from root node all the way down to the leaf nodes. We have explained the intuition why doing this ensure that every new message can be computed right away, right? Namely, all the dependent messages are there. You don't need to wait for the dependent messages. Right? So, but that's just the part. The original sum product algorithm is just developed to calculate the marginal distribution for every node in your graphic model. And in practice, there is another important problem that is given the joint distribution over this graphic model. Right? We want to find out the configuration of all those variables or nodes in this graph that maximize the joint probability. So this is important for many structure prediction problem. We used an example in NLP, like speech tag of speech, speech of tag, part of speech tagging on a sentence, right? So if you have a sentence like this is a cat, right? So you want to tag the word type of each word, right? So obviously you can construct, if you will, each word, their tag as a random variable. A very commonly used graphic model will be a chain structure graphic model. And we want to tag the type of those words along this chain. You essentially, in the Bayesian or probabilistic model framework, you want to find out the configuration of these four variables which maximize the joint probability. So to do that, we can actually explain in the last lecture, we can view as a special application of the sum product algorithm. How can we see this point? So first of all, if we want to maximize the joint probability, it is essential to maximize the log joint probability. It doesn't matter because if x star maximizes p of x, it also maximizes logarithm of p of x. So, and then that means your maximization is over the summation of the log factors across the whole graph. Right? So you can see the naive computation of this maximization has the same structure as we have done to calculate the marginal distribution. Right? To calculate marginal distribution, well, we want to we first multiply all the factors across the graph, and outside of the product, we sum over the remaining variable nodes in the graph. So in the maximization problem, in the inner level, we sum over all the log factors across the graph. And then in the outer level, we just doing the maximization over every random variable node. So you can see they both have this structure. The first problem is just the sum over the product structure, right? A second problem is maximization over the sum structure. The key observation is that if you're doing maximization over sum, the distributive law still applies. And remember, our original sum product algorithm, why it is efficient, why it is accurate, because this max and product operation also follows the distributive law. So the key is that they obey the distributive law, not depending on how you implement sum, how you implement product. So we found that we will actually do maximization over the summation. They also follow the distributive law. That means we can use exactly the same algorithm steps in the original sum product to maximize the log joint probability. How can we do that? Imagine that you have implemented your sum product algorithm, but now we just overload the sum operator and the product operator. So to implement the sum operator, we just fulfill it with maximization. And to implement the product operator, we just fulfill with summation. So that's it. And in the C++ framework, we know there's a functionality is called operator overload. So you can imagine if you implement some product algorithm, right? You have defined some operator sum and product. Of course, by default, they're going to conduct algorithm summation and algorithm product. Right? But now, if you want to find the maximum log joint probability, you can just redefine the operator, these two operators. Right? In your redefinition of this operator, you're actually conducting maximization. In your implementation, in your redefinition or re-implementation of this product operator, you are essentially doing sum. That's it. And this is what I implemented, how I implemented a general graphic model inference algorithm. I have implemented a general graphic model inference algorithm and put it on open source library like 12 years ago. This is just how I did that. Does it make sense? Yeah, of course. Yeah, because your actual computation changes, right? It's just like the whole algorithm flow and the operation flow is the same, but the actual computation is different. Right? But I mean, to find a maximization, it's just to follow that same procedure. Other question? Okay. And if you look at the message computation, right? So initially, because now it becomes log fact, you take a logarithm of the factor. So initially, message, if your leaf node is a variable node, then the message is initialized as 0, which is logarithm of 1. And if your factor node is a leaf node, if you want to compute the message from this leaf node to its variable parent node, you just take a logarithm of f of x, and then this is a corresponding rule to compute the messages. Okay, so you can see that in the original sum product algorithm, this is just a summation, right? This is just the product, and now we just fulfill the summation by maximization and product by summation. Of course, the factor has to be changed as the logarithm version. And similarly, if you want to compute the message sent from a variable node to a factor node, right? So in the original definition, they're just the product of the messages sent from all the other neighboring factors to x. Right, but right now, the product is actually fulfilled by summation. That's why we become summation.
So implementation. Is a table.
This message is a table. Yeah, yeah. Yes, exactly. Yeah.
So what if we are dealing with continuous?
Yeah, that's a very good question. In continuous, unfortunately, if you don't have closed form of this, it won't be feasible. Okay? Unless like you can do this, you can like doing this, you can this is still maximization. I mean, if you do the sum product, they will become some integral, right? You need to ensure that the integral is analytically tractable. It has closed form. Otherwise, you won't be able to do that. And then we have to seek for some approximate inference algorithm, which will be our next big topic. Any other question? Okay, the last thing we should be aware is that if you just reuse the sum product algorithm we have implemented, you can only compute the maximum log joint probability. Okay? So you follow the first pass from the leaves to the root, and the second pass, you distribute the message from root to leaves. And then once you have calculated all the messages, you can pick up any node as your root node. And then to find out the maximum, this should be logarithm. So to find out the maximum log joint probability, you just sum over the messages sent from every neighboring or child factor to x, and then maximize the summation with respect to x. And of course, you know that this particular variable x, taking which value is going to maximize the log joint probability. But here comes a problem. In most cases, we're not only interested in finding the maximum log joint probability. We also want to know which values of each variable takes can maximize that joint probability. Right? And here we can only find one variable whose value that maximize the log joint probability. Right? But how do we find out the optimal configuration of all the other variables which maximize the joint probability? Any thought? What?
At the bottom, it is clear. It's back. At the end, we have a table which we can find which variable is maximizing the.
Yes.
Then in that table we can find the previous one, and get back to the
Yes, exactly. Yeah, very good. So as what he just said, we can track not only the message value itself, but also at which particular value you calculate this message, right? So when we look at our message calculation, every time we know that, okay, if we want to compute the message sent from a factor to a variable node, we're going to maximize the factor itself plus the incoming message from the child variables to f, right? So then we maximize over its children nodes, x1 to xm. So of course, calculate that, we're going to get the message value itself. At the same time, we're going to find which particular x1 to xm maximize this. Right? Is actually track the configuration of its child nodes, which give you this message. Then that's it. Okay. And then you can imagine that, okay, when we find at which value x, we have the margin, we have a maximum log joint probability. I say x equals to 3. Okay? And then based on the setting of x here, we can track the messages, right? For example, this this is x1, right? So we know that mu x1, we know that mu f to x, and here x equal to 3. We know that when x equals to 3, which set of x1 to xm here is gonna give you this message. Then you know the optimal configuration of x1 to xm. Okay. And then you just recursively trace back until you reach all the leaf nodes. That's the way how we efficiently find out the optimal configurations of all the variables in this graph, which maximize the log joint probability. Does it make sense? So let me summarize, right? How to find the global configuration x max, and here remember x max include x1 to perhaps xn, right? And that gives the maximum joint probability. Right? So to do that, to efficiently do that, we need to store a quantity to tell how to trace back to the variable value that maximizes the previous subproblem. This is called backtracking. Okay? So this can be done by storing a little bit more information. Every time when you calculate a message, you not only maximize those things, right? This incoming message plus the log factor. You also store which particular value maximize that. And then you can use the distribute procedure, right? Like how we distribute message from root to all the leaf. Use same procedure to try to trace back the optimal configurations of all the variables. So each message implementation can contain two components. First, the max sum value. Second, the variable value that gives the max sum, namely argmax. Any question? Does it make sense? Okay, so for example, this is just an illustration. It's not necessarily represented. I give the comprehensive representation, but you can imagine that. Okay, for this is a one variable, right? So we know that when xn plus 1 equals to 3, k equals to 3, it gives a maximum joint probability. Then we trace back the message sent from here. We know that when xn plus 1 equals to 3, and this message value is computed when xn equals to 3 as well. And then you can trace back, this is actual factor. You know that the incoming variable node, xn minus 1, it will take 2 to calculate the message, this factor sent to xn, which when xn equals to 3. And then you just keep continuing trace back, right, until you get xn plus 2. You know that xn minus, when xn minus 1 equals to 2, and the value of the optimal value of xn minus 2 will be 2 to calculate the message when xn minus 1 equals to 2, and until you reach the leaf nodes, you cover all the leaf nodes. So here I just want to draw a connection to dynamic programming. So if you're very familiar with dynamic programming, you see that this is essentially smart trick of conducting dynamic programming. And if you're doing some computer coding computation, right? There's dynamic programming is often a common used trick, right, to improve the efficiency. And if your vector graph is a chain structure, like hidden Markov model, then the max sum algorithm has another name. It's called the Viterbi algorithm. It's a very classical and very well-known algorithm. Okay, any questions so far? Great. So now to wrap up, we have introduced a broad family of the probabilistic models, which are represented by graphs, right? So what we expect you to know is that what is the definition of vector graph, right? And what's the sum product algorithm? Like what's the key idea of that? And how does sum product conduct message passing? Right? And what's the definition of messages? Message essentially is the summation and marginalization over a particular subtree in the graph. Okay? And you need to know that for the tree structure graphing models, sum product is not only efficient but also accurate. But when your graph has cycles, it does not guarantee to be accurate anymore. But if and in this case, the sum product is called loopy belief propagation, and it does. And the loopy belief propagation even does not guarantee convergence. But usually, if it converges, it works really well. And then we talked about a variant of sum product algorithm is called max sum algorithm. Max sum algorithm is essentially an efficient way to find out the configuration of the variables which maximize the log joint probability, which is very useful in structure prediction problem. And finally, we expect you to be able to implement this algorithm yourself. Mm-hmm.
apply general graphs.
You can apply that, but again, it doesn't guarantee you really find the maximum.
Not looking for guarantee. You said in the propagation when it converge, it's often good.
Yes.
So for max probability, you have to say.
No, that's not guaranteed. Because for loopability, I would rather say this is a kind of open problem. I wouldn't say it's rather good, because for loopability propagation, there are theorems showing that if you're doing some product in that way, in a cyclic way, and if it convergence, it is essentially to solve max-min problem, solve a minimax problem. And solve a minimax problem, a very complicated objective function. But this complicated objective function is defined totally on the structure of this graph and the factors. So people call this as the energy function. So, well, that means once you converge, you're gonna solve this problem. That means you arrive some saddle point here, because this is a minimax problem. So it's kind of a local optimum, but it usually works well. But for maximum, I mean, in general, I don't know what is the objective it corresponds to. Maybe if you define some general sum operator and more abstractive sum operator, more abstractive product operator, it still corresponds to some objective function. But I would rather say, to my knowledge, is rather open than saying and not giving any conclusion. Other question? Okay. So now we're gonna start with oops. We're gonna start with another topic. Okay. Oops. Let me. Sure. All right. So from today, we're gonna start talking about another important thing regarding the computation, right? So which we generally call it approximate inference, right? So and before we continue, let us just look at what we have discussed so far. So at the beginning, we have looked into a bunch of foundations about the probabilistic machine learning, right? Including all kinds of distributions, priors, conjugate priors, uninformative priors, exponential family, and their properties, and so on. We said that based on those foundations, we can build our own models. So we can do the calculation, the prediction, and so on. Right? And then we introduced two families of very commonly used probabilistic modeling tool. One is called generalized linear models. The other called probabilistic graphic models. So, and by the way, these two family of models are not non-overlapping. Actually, they kind of like largely overlap, but we just introduced them with a different angle. So for the generalized linear models, we just highlight, okay, there is some like linear structure inside a model. That does not necessarily mean it is only linear model. Right? You can introduce a variety of nonlinear transformation, nonlinear feature mapping to construct very complicated nonlinear models. And another is that, okay, we're going to use a graph theory. We use graph tool to describe our model. And later, we're going to talk about the two very popular and very important specific models, which can be viewed as the instances of these two family of models. One is called Bayesian neural networks. And we actually mentioned that before. Bayesian neural network, especially the feed-forward neural network, can be viewed as a special case of generalized linear models, and also a special case of probabilistic graphic models. Depends how you view the model, right? And also Gaussian processes. Gaussian processes is you can view as the extension of generalized linear models to the functional space or infinite dimensional space, and it has a very strong correlation with Bayesian neural networks, which we're going to discuss later. See that if you make your Bayesian neural network have an infinite wide or infinite number of neurons in one layer, and then the posterior, it converges to the Gaussian process. It's a very well-known theoretical connection between the two types of models. But we have already talked about a lot how to model, right? How to construct a probabilistic model. Right? And when we have the data, we have observations. Of course, another important thing is how do we conduct computation? And if we only have modeling tools, it's useless. Right? You need to be able to compute. Given the training data, given whatever test data, you should be able to estimate those model parameters. You should be able to make predictions. Right? Otherwise, what's the usage of the probabilistic models? Right? So before we come to these two specific models, we're going to first talk about the computational technique used in probabilistic machine learning. So, and usually we call it approximate inference. The reason is that in most cases, in most practical cases, we won't be able to give exact computation. Like the scenario where we can apply some product algorithm is really limited. Like someone has mentioned that what if you have a continuous random variables in your graphic model, right? Then your message passing, you calculate message, you have to integrate out all the variables in the factors, right? And if you have a non-trivial factors, usually that integral is intractable. So in most cases, we have to resort to some approximation to seek a trade-off between the accuracy and efficiency. So this is actually kind of art of probabilistic learning. Like you have a perfect modeling too. You can model whatever things in a rigorous and principled mathematical framework. However, the computation is a nightmare. You can never guarantee your computation is right. I mean, in most cases. So we're gonna mainly introduce three type of strategies to do the approximate inference. The first one, perhaps is the simplest one, is called Laplace approximation, which is really straightforward. You see that all you need to do is to conduct map estimation and then compute the hashing of your log joint probability. And then we'll introduce the two large family of approximate inference algorithms. One is called a variational inference. So it is called a deterministic approximation algorithm, meaning that, okay, there's no asymptotic guarantees, meaning that no matter how you increase the number of training points, whatever, it always has a gap between your estimated posterior distribution and the true posterior. Unlike the Markov chain Monte Carlo sampling, which is has much longer history than the variational inference. The benefit of Markov chain Monte Carlo sampling is that, okay, it has some asymptotic guarantee. It is unbiased in that as long as your chain runs enough long, and when your chain enters into the stationary state, it guarantees the distribution of the state will be the exact posterior distribution. But the problem is that for MCMC, you usually don't know when your chain arrives at the stationary state. That's like, it might be very quick. It might be very, very long, maybe 1,000 years. And even worse thing is that people don't have a exact tool to tell when it reaches stationary status or not. So we have some like diagonal tools, but it's only heuristic, and practical is not like theoretically guaranteed. So that's a problem. That's a problem. So and also the bottleneck of probabilistic learning. Like you have a bunch of beautiful tools and powerful tools to design all kinds of models, but you have to invent all kinds of approximations to get reasonable results. Okay, so what's our plan for the next step? We'll discuss approximate inference schemes that will span our quite a few lectures. Then we'll give examples about how to apply these schemes. And finally, when we know the idea of those computation tools, we'll give some specific models. And here we plan to use the classical topic models called latent derivative allocation, which is very hot about 10 years ago, and to showcase how we apply those inference algorithms to calculate the posterior distribution and make predictions and so on. Okay, so this is an outline. So Laplace approximation, and then variational inference, and then Markov chain Monte Carlo sampling. And if we have time, we might be able to introduce the so-called expectation propagation. So that is to address the problem just right. What is if you have a continuous one variable, you are not able to exact compute a message? Then what kind of things will propagate? We're propagating not messages, we're propagating expectations or means under the exponential family approximations. But that is dependent on our time. Okay, so for this big topic, we expect that you will capture the key idea of those algorithms, and you will be able to implement those approximate inference algorithms for a few well-known models, including Bayesian neural networks. And in the remaining section, we'll see many practical tasks. Okay. Any questions so far? So now we're gonna talk about the Laplace approximation. Let me try it again. Okay, we're gonna first introduce Laplace approximation, which is the most straightforward one. And we will use Bayesian logistic regression as an example to show how we apply Laplace approximation to calculate posterior distribution of the weights, and how we incorporate this posterior distribution of the weights to calculate the predictive distribution. Remember, the predictive distribution is let me expand, right? So suppose this is your training data, right? And for a new task, the input, suppose this is your label, prediction of the label, right? So the predictive distribution is the distribution of your prediction given the training data. Right? So this is not like, suppose I know the model parameters, the weight vector W, I make a prediction. It's actually marginalized out the posterior distribution of W. Right? So just write it down to help you recall that, right? So we know that for any particular parameter vector W, right, we can make prediction about the label Y star, right? But then we consider all possible W, and under the posterior distribution of the W. That is called predictive distribution. The benefit of predictive distribution is that, okay, we consider all possible W and weight those W's according to their posterior distribution. In this way, you can make a more robust, more accurate prediction. Okay, this is benefit, and this concept is not in non-probabilistic methods. Okay. So now let us first look at what is Laplace approximation. So the objective of a Laplace approximation is straightforward. Now that I don't know what is the posterior distribution, I just assume it is Gaussian. That's it. Very, very straightforward, very brutal. I just assume it's a Gaussian distribution, and we assume this Gaussian distribution approximates the posterior distribution, right? So then the question is, how do we know what is the mean and the covariance of that Gaussian distribution, which approximates the posterior distribution? That's what the Laplace approximation aims to address. So the method is that we're going to apply the second order Taylor expansion at the posterior mode, namely the map estimation. Let's see the detail. Right? So suppose this is our joint probability. Right? Theta are the random variables, which might be the model parameters and so on. Right? And D is the training data, which are the observed random variables. Right? So our general goal is to compute or approximate the posterior distribution of theta given D. That's our general goal. And Laplace approximation will first do a map estimation. Namely, I just take a logarithm of log joint probability and maximize this log joint probability. That's map estimation. You can use whatever optimization algorithm you like LBFTS, like stochastic gradient descent, conjugate gradient descent, whatever. Right? And suppose after this optimization, you get your optimal value of theta, which is denoted by theta 0. We know that theta 0, at theta 0, your log joint probability is maximized, and meanwhile, it means the posterior probability is maximized as well, right? Because the posterior distribution is actually proportional to the joint distribution, right? It's just divide the joint distribution by the model evidence P of D. The P of D has nothing to do with theta, so it doesn't matter. So, so now, what's the usage of this map estimation? We're gonna expand the log joint probability at the posterior mode, namely the map estimation. How can we do that? Right? If we just will the log joint probability as a function of theta, it's just a function of theta, right? And according to Taylor expansion, right, we can expand f of theta at any point we want. So here we just expand theta at theta 0, namely the map estimation. And then we use second order expansion just for convenience. So then we can write that f of theta is approximately f of theta 0, evaluated as theta 0, plus the gradient of f at theta 0 in the product with the difference between theta and theta 0. Okay? And plus this second order term, which is a quadratic term, right? It's half theta minus theta 0 transposed with this second order derivative of f at theta 0 and times theta minus theta 0. Okay? So this is second order term. So this is just a application of second order Taylor expansion. Right? But here is a key observation. Remember, theta 0 is map estimation, meaning that at theta 0, your log joint probability is maximized, right? So that means the gradient of f at theta 0 is simply 0. It is optimal. It's optimal, then the gradient must be 0. That means this term is simply 0. Right? So we only left this f theta 0 and this quadratic term. Okay? And another observation is that because theta 0 maximizes the log joint probability, that means the Hessian, the second order derivative of f at theta 0 will be a negative semi-negative, semi-negative definite. This is a basic property of the optimization. You can find it from any optimization book, and it's not hard to prove. If you want to prove that, just use the exact Taylor expansion and use some, I guess it's invalid theorem or whatever. You can show that. So basically, if you find a local minimum of function, then at this minimum point, your Hessian will be always a positive semi-definite. If you find a local maximum, local maximum meaning not necessarily the global maximum, then your Hessian at this local maximum is also a negative, a semi-negative definite. So this is a basic property. So that means we can rearrange our second order Taylor approximation in this form, f of theta 0 here, right? And here A is defined as minus Hessian. So because Hessian itself is a semi-negative definite, so it's minus, which is A, will be semi-positive definite, right? So now we have our approximation. So f of theta, which is defined as a log joint probability, is approximately f of theta 0 subtracted by this quadratic form. And remember, f itself is a log joint probability, right? So if you want to get the approximation of the probability itself, we should just take exponential. Okay. So we get our approximation of the log joint probability as exp of this guy, right? Sorry. And e to the power of f theta 0 essentially is the joint probability at theta 0. And this guy is e to the power of minus half, this quadratic term. So now, what's that? Mm-hmm. Mm-hmm. Oh yeah, you're right. It should be negative semi-definite. Yeah, semi-definite. Yeah. Yes. So in the next slide, what we get is not Gaussian. Yeah, that's a trade-off. Like you either will as a deteriorate Gaussian, or you usually add a small diagonal matrix to make this a positive definite. Yeah, you can view it as regularizer, but this is just some practical trick. You always, in practice, you always add some like epsilon times identity to ensure this guy is always a positive definite. Okay? Or you can do that as well. Like one other way is that, okay, if A is just a semi-positive definite, meaning that there are some zero eigenvalues, right? And then you can do the Eigen decomposition, and the Eigen decomposition now becomes like VI transpose times the eigenvalue, like sigma I. Right? You actually multiply the eigenvector to this guy to do some linear transformations. You actually approximate the linear transformation of those thetas. There are two ways of doing that. But what you're saying is right. More rigorously speaking, this should be a semi-positive, semi-negative definite, and here is semi-positive definite. Okay. So now, if we take exponential, we immediately find that this joint probability can be approximately as a factor, a constant factor, times this exponential term, right? This exponential term happens to be a Gaussian term. Now, how do we compute the posterior distribution? If you base on this approximation form of the log joint probability, you even do not conduct any explicit normalization. You know this is Gaussian. So according to this approximation of the log joint probability, you immediately get approximation of the posterior probability, which is a Gaussian distribution. And the mean will be the map estimation, right? And the covariance will be inverse of A. Right? Remember, A is the negative Hessian of the log joint probability. And now we go back to the point we just mentioned. Of course, if A is low rank, is not full rank, then A inverse is not feasible. Right? So in practice, to ensure A is always positive definite, you're gonna add some small diagonal matrix to A to ensure this is positive definite. Or you can even first do the Eigen decomposition and pick up it's not like in some numerical, there might be some numerical issues like when you optimize, you're not exactly find out the optimal point. So when you decompose A, you even find some small negative eigenvalues. It is possible. Because in theory, when you arrive at the minimum optimal point, you must guarantee that your gradient 0 and your negative Hessian is positive semi-definite. But when you run algorithm, it's not always the case that you're gonna arrive at that point. So it is possible that you have some negative eigenvalues from calculate. That's why in practice, people always choose appropriate diagonal elements to ensure when adding this, you have a positive definite matrix. Any questions so far? But the idea is relatively straightforward. Right? It's just to run the map estimation using whatever optimization algorithm you want, and then expand your log joint probability at the map estimation, and then use the Hessian to approximate, actual Hessian inverse to approximate the covariance matrix. That's it. So although it looks surprisingly simple, it works pretty well in practice. So, for example, here is one concrete example where our probability of Z, our density of Z is approximately is proportional to this guy. We didn't calculate the normalization factor or normalizer, but it's proportional to this exponential term times a sigma function of 20Z plus 4. So if you draw the true density, it is a yellow curve. And now, if you apply the Laplace approximation, remember Laplace approximation will first define the map estimation, right? It's here. And then at the map estimation, you just calculate Hessian of the log joint probability. You use Hessian inverse to approximate the variance. So it will always give you a symmetric Gaussian approximation. So you can see that, of course, they're not overlapping. This guy is not the yellow one. The ground truth is not obvious. It's not Gaussian, but you use a symmetric Gaussian approximated, and it's quite close. In most cases, this approximation is acceptable. But some recent work, I think in SAR 2018, there are some papers talking about using Laplace approximation to calculate posterior distribution of Bayesian neural network. They have a bunch of approximations, and it looks like they're working well as well. Okay. Any question regarding the framework for the Laplace approximation?
Is more resistant against noise.
Yes.
Can you replace Gaussian to estimate just instead of using?
That's a good question, but for the Laplace approximation, I doubt you can use Laplace approximation to do that. Meaning, because if you do the Taylor expansion, second order Taylor expansion, it always gives you a Gaussian form. But we have other ways, like variational approximation. And then you can specify your approximate posterior is parameterized student t distribution. They're going to optimize that parameters to make your student t approximation as close as possible to the true posterior. That is doable. Okay. Any other question? Okay, now let us look at a particular probabilistic model, namely Bayesian logistic regression. Right? We have talked about that before when we introduced general linear models, but in that discussion, we only introduced how we conduct MLE, right? Or map estimation. We use Newton-Raphson update, right? If you have already started homework 2, you see that some problem encourage you to solve to get map estimation of Bayesian logistic regression using Newton-Raphson updates. So from today's lecture, you see that once you get that map estimation, you also be able to construct the posterior distribution of your weights and calculate the predictive distribution. So what is Bayesian logistic regression model? A quick review. So suppose we're given a data set where phi n is your feature vector, right? After some kind of transformation, of course, if you don't do any transformation, it's just absent. And they're labeled. And this is a binary classification problem. So your label Tn is either 0 or 1. And suppose you have collected big N data points. Then we first assign a Gaussian prior distribution over the model parameters, namely V vector W. And here M0 is often chosen to be 0. And S0 is often chosen to be a diagonal matrix, like some small s times identity matrix. But in general, you can use whatever M0 and S0. And then given the width vector W, right, how do we generate the labels? So first we assume, okay, given the model parameters W, the width vector, each label is sampled independently. So each label is sampled according to this Bernoulli likelihood, a Bernoulli distribution, where Yn is the probability your label is 1, right? So 1 minus Yn is the probability your label is 0. So the likelihood will be this probability Yn to the power of Tn. Tn is the actual observation, right? Times 1 minus Yn to the power of 1 minus Tn, right? So here, the bolded T represent this N labels, right? And the Yn is the probability according to the current model. What is the probability the label is 1, right? Which according to the logistic regression is just sigmoid function of this prediction score. Prediction score is W transpose phi n. Any questions so far? This is just a quick review of the logistic regression we have discussed before. And then we know that given the training data, right, namely the observed labels for all the n examples, the posterior distribution of the weight vector W will be proportional to the prior of W times the likelihood of T given W, right? So now let us apply the Laplace approximation to calculate this guy, right? So we know that we need to first maximize the log joint probability to get map estimation, right? So we take logarithm of log joint probability. So this is a log prime, right? Log P of W. And this is a log likelihood of the labels T, right? If you take a look at here, you take a logarithm over this, which is a sum over N, right? And inside each sum is log of the Bernoulli, right? And we can leverage and we can use Newton-Raphson methods to get the optimal W, right, which we denoted by W map, right? Or you can use whatever other optimization techniques like the LBFGS, whatever. In our class, we have talked about how do we conduct the Newton-Raphson update to get W map. Right? And once we get the map estimation of W, we're going to take the negative Hessian over the log joint probability, right, at W map. And if we take the negative Hessian at W map, it will give this, right? So it is inverse of the prior variance S0, prior covariance S0 to the power of -1 plus this guy. This is just a copy of the previous result. And here Yn is the sigmoid of W map inner product with your feature vector, mapped feature vector phi, right? Remember, it's evaluated at the map estimation, which is the probability on the map estimation of W. Your Tn is 1. Right? So now, given the map estimation and the negative Hessian of the log joint probability at map estimation, we can construct a Laplace approximation of the posterior of W, which is Gaussian, right? Mean is map estimation, and the covariance is the inverse of the negative Hessian as often. Just follow the steps of the Laplace approximation. Right? So, any questions so far? Yeah. Remember, in our previous discussion, we maximized this guy by using Newton-Raphson update, right? And we also mentioned that you can use other gradient-based optimization techniques to find W map. So now, let us consider, given this approximate posterior distribution of W, how can we calculate the predictive distribution for any new input? So, given a new input phi, so first of all, before we look at the predictive distribution of the label, like say T, right? Let us first look at the prediction score. We know the prediction score is just the inner product between the input and the weight vector, right? And we, from Laplace approximation, we have already obtained the posterior distribution, which is a Gaussian. So, and then we know that A is just the phi transpose W. From that, we can obtain the predictive distribution of the prediction score first. Okay. And we know that any linear operation over a weight vector over a Gaussian random variable is not a Gaussian random variable. Right? So we can immediately get this. That is the predictive distribution of the prediction score A given the training data will be another Gaussian. Right? The mean will be inner product between W map and phi, and the variance will be phi transpose as an inverse phi. And this is a prediction of the, this is a predictive distribution of the score. But now our goal is to compute the predictive distribution of your label, right? Like y, not y. Y is not good. Like I use this theta t given the data, right? And here is the vector t. Right? So that means we have to consider another integral. Right? So because given a prediction score, right, which is from a predictive distribution, right, the probability that your label takes C1 will be a sigmoid function of your prediction score, right? And if you want to compute the predictive distribution conditioned only on the training data, you have to marginalize out this prediction score as well. That's why you have to do an additional integral. So here we know that the Q of A is a Gaussian, right? And the sigmoid is sigmoid function. So the integral of the sigmoid multiplied with the Gaussian is analytically intractable. But the good thing is that because the score itself, for a particular example, is a scalar. So this one-dimensional integration can be easily calculated by the so-called numerical quadrature. Like typically, Gaussian quadrature can give you a very accurate approximation of this integral. In this way, we are able to compute the predicted distribution of your label takes 1 or takes 0. Any question?
Just assume that we apply logistic regression. I don't think practically in real world, and if we apply logistic regression to this defining value. This is one way. The other is Bayesian logistic regression and do this approximation again for each given feature, we do this integration and then find the label. This method is working really well. Much more just
it's not much more, it's just an additional step. Right? If you do logistic regression, you still need to do some kind of map estimation. Right? And then you use map estimation, you use this W, and then you just calculate the output of a logistic function. Yeah.
It's not, it's one is just computing. Not computing.
Yes. Yes. Yes, it's of course it's easier.
So I want to know what's the benefit of this? Is it really working better in practice?
Yeah, it's more robust, and also you will know the label, the distribution of the label itself. Like this is data, right? This is a Bernoulli distribution, right? And it's there's a funny thing that if you don't use Bayesian stuff for that, like even you use logistic regression to calculate the probability 0.6 or 0.9, you might still have a large uncertainty on that. So that's not like, okay, I calculate a logistic function over your score to give a probability. That probability is not guaranteed to be good. Like you have this probability, but your uncertainty can be quite large over that. But here, if you use this framework, it tells you, even for your score and for your finally predicted probability, what is the variance, what is the what is the confidence interval.
Much more information.
Yeah, you have more information, you are more robust. And for this method, actually your additional cost is negligible. Because what you do is, okay, once you get W, you just calculate the hashing, right? And this is hashing, if your W is not very high dimensional. If your W is very high dimensional, you have to approximate hashing like block diagonals, not full diagonal. But anyway, this additional cost, right? You do this integral and using numerical quadrature, they're all very fast. But if you want to do more accurate calculation about posterior distribution, you have to involve other methods like Bayesian inference, like MCMC. It will be a lot more costly. But this is actually more robust and more accurate in practice, especially when your data contains a lot of noises. And also, there's one paper, I think it was very good explanation of that. It's called dropout or variational dropout. So they explain dropout essentially is a way of performing Bayesian inference on that, and they use the logistic link function as an example. Like you want to do the classification, like even if you don't do any Bayesian inference, you do binary classification, you classify this is a cat has a chance of 0.8. That really doesn't mean your confidence that this is a cat is 0.8. Because if you're using Bayesian, you found that, okay, this is just your prediction. And surrounding this prediction, if you calculate the predictive variance, it can be large. That means your actual confidence for this particular image is a cat or not is not as large as you can see from the single prediction. If you're interested, you can take a look at that paper. That gives you much more detailed explanation. But maybe you guys will ask why I care about this uncertainty. Well, it's pretty important. For example, for example, if you want to do the recommendation. So, like you are a user, right? You have a registered account in Google, you have a registered account in Amazon. They are always trying to recommend you some advertisements, some new products. So there is a annoying trade-off like between the exploration and exploitation. So basically, once you buy something, you do something, they kind of model you. They collect your information, they're gonna model you. You build up a personalized model. So now every time when you see a web page, and depending you yourself and also the web page content, they're gonna predict how likely you will like each candidate advertisement or products. And then there's a problem like, what if I don't know if you like it or not? Like if you, for example, my model tells me you only have 60% chance to like that product. And then there is a trade-off like, should I just give you a totally brand new product to, to irritate your, not irritate, to stimulate your interest for new products, or I just recommend you this product. And if my model tells you, okay, I don't have any uncertainty about your preferences, and you like it very much, now I will give you this. But you can imagine that if you're always doing that, like you purchase 3 iPhones, right? If I always recommend iPhone to you, you won't like it. You get bored. We're human beings. We're always trying to see some new stuff. Right? So there are some cases like, suppose I try to recommend Galaxy phone to you, but my model tells you, okay, you don't have that charm, you don't have that preferences, that high preferences of to like that advertisement, or my uncertainty about whether you like it or not is high. Then I'm gonna random pick up a new product and send to you. Maybe it's I don't know, maybe some food or whatever. Right? So in this case, when do you want to recommend new products or recommend existing products? The right time is very important. Otherwise, the customers will either get bored about products very soon, or feel like this recommendation system is not accurate. It's recommend me garbage. So yeah, this is very important because they hire like thousands or tens of thousands of talents to earn your clicks. The more even they improve 1% chance of clicks, they earn like $1 million every day. This is extremely important. Not to mention other, but there's some applications. I know how this uncertainty is applied. Okay, so we have a finished introduction of Laplace approximation. So we expect that you know the general idea of Laplace approximation. You will be able to implement. Okay, thanks. And let's stop here a little bit early today, and I hope everyone has a great spring break. Okay, yeah. See you guys.